I should have said last time, and I will say it this time now, that, I put these slides together with the idea that they'll be posted and accessible. So if you are desperately trying to scribble things down, if you are trying to catch up here, then taking notes isn't bad, but it might, I assure you, you will have access to the presentation, and this one has even more, things to copy down, and so it might be good to assure you to rely on the slides to provide you that information. So let me talk about interferometry. It's funny that Deepti left off where she did, because she talked about the antenna illumination pattern. I think I'll just skip my first couple slides, but I thought it was an interesting introduction to Fourier transforms in radio astronomy is the derivation of the antenna power pattern, which you can do, which I will not do because she gave away the answer. She stole my punchline. You can come up with the Airy pattern, or at least the sync pattern, by considering a simple one-dimensional problem of a transmitter or an antenna receiving that's just a line, and adding up the contributions all along the line to the electric field at a distant point A. And when you do that, if you step through it, what you'll find is that you have an equation that looks like this, that you have the electric field out on the sky there. I'm trying to remember which, yes. The electric field out on the sky there is being the amplitude of the electric field along this antenna Fourier transformed. And so the antenna beam pattern on the sky turns out to be the Fourier transform of the electric field illumination pattern of the antenna. And this is really quite useful. In the simple case, which is that one-dimensional line, you've got that top hat function, and its Fourier transform is the sync. This is the electric field pattern on the sky. The thing we think of as the point spread function in optical astronomy is, of course, not an electric field pattern, because you don't sense electric fields in optical astronomy. You're gathering photons. So it's a power pattern, and it's the square of the sync function for this one-dimensional case. But this is really useful because in radio astronomy we have much more complicated effects than just top hat illumination. In fact, we almost always taper the way we illuminate our antenna because it's nice to get light from the entire aperture, but it's not great to have light coming from past your aperture. So if you're fully sensitive to the edges of your dish, you're probably sensitive to some power beyond it. And so in order to calculate the sky, the beam pattern you expect on the sky when you don't uniformly illuminate your aperture, it's good to have this simple Fourier transform relationship. Moreover, we have blockage in our telescopes, and we have surface errors, and we have gaps between panels, and so on. And all of these effects can be handled by just realizing that you can Fourier transform from the field pattern in the aperture to the sky beam pattern. Okay, so to interferometry. Let's talk about why we're bothering to do interferometry, which is the combination of separate radio dishes into one big radio dish. And the simple answer is that if you want to make a more sensitive telescope, you want to get a bigger telescope to gather more of the watts per meter squared, or hertz. But the size you can make your telescope is fundamentally limited by the strength of steel and carbon fiber and your budget and so on. And moreover, the telescope size that you can achieve is related to the accuracy with which you can render the surface you're trying to build. The paraboloid you want will not be perfect. The bigger it is, the stiffer it has to be over a larger area in order to achieve the surface. And if you misshape your surface, you start to lose your sensitivity. And beyond that, if your telescope is very big, you have to point it even more accurately because, as we just said, the aperture pattern is the Fourier transform of the beam on the sky, and as Deepti just said, due to the similarity theorem, the bigger your aperture, the smaller your beam on the sky. It's a property of the Fourier transform. And so if your beam is very small in the sky, you have to take your really big, really expensive, really precise dish and point it even more accurately in order to get what you want out of it. And even if you make a really big dish, the resolution you can achieve in radio wavelengths is unimpressive, right? The resolution of a radio telescope in useful units is about 2 arc seconds for a wavelength in centimeters and a diameter in kilometers. And there are not a lot of telescope diameters in kilometers. And so if you want the sort of arc second resolution we're used to as a baseline astronomical capability, it's hard to get there. The biggest telescopes we have are, you know, they don't quite round to kilometers, but they're, you know, they're of that order. Here's Arecibo. Its surface is nice and clean, which is nice to see. This is a recent picture, though the feed is broken off from the hurricane. But it gets you, you know, to 30 arc second resolution. There's many of us in front of FAST last year. It's 500 meters across, although not all of it's illuminated, and it'll get you to arc-minute resolution. These are really big telescopes, and they're not giving us that sort of arc-second resolution we'd hope for. This is a millimeter telescope that's 50 meters across. This is actually getting to several arc-seconds of resolution, and that's, you know, that's quite impressive. This thing is a feat of engineering, no doubt. It is a difficult structure. We use it in the Event Horizon Telescope, and all of that steel is very sensitive to temperature, and the pointing and the surface efficiency and the focus are you know, reflected or show us that every time the sun comes up. This is a you know, physical demonstration of the limits of how big you can make a telescope. This is the NRAO 300-foot telescope. It predated the GBT, and then it did that. And so, you know, going much bigger than this is hard. And I never miss an excuse to opportunity to show this picture. No one was killed. And so why interferometry? It's because we can get that higher resolution and we can get that higher sensitivity. You can assemble more collecting area if you don't have to put it all in one 300-meter aperture, right? So if you can find a way to connect discrete small apertures, I mean, if you could imagine the limit where all you had to do was, you know, take everyone in this room and have them hold up a big feed horn and point it at the sky and combine them, that would be nice. The receiver costs at some point start to make that not favorable, but there is an optimum between making one big telescope and making a lot of little ones. You can see this in this plot. This is the effective area, which directly connects to the sensitivity. If you take low frequencies, the VLA is bigger than the GBT, even though it was built beforehand. The efficiencies of those telescopes roll off before the GBT does, though, because their surfaces aren't as precise. And so at some point, the GBT becomes larger. ALMA, which was built yet later, exceeds, even though in pure geometric area, it's not bigger than the GBT, because you're building your ALMA out of a bunch of 12-meter dishes rather than one 100-meter dish, you can add up to much more effective collecting area over a much wider wavelength. You don't even really see the roll-off of the aperture efficiency. So interferometers can get us the sensitivity we want. They can get us the resolution we want. They inherently give us a large number of resolution elements per field of view with only one detector per telescope. So rather than having to build a big camera and scan it across the sky, you just put one detector in each telescope and you synthesize a lot of beams. I'll talk about it a little bit later. You can achieve much higher astrometric precision with interferometers because rather than determining where a source is on the sky by precisely pointing your telescope to a fraction of an arc second, which is a very tricky thing to do, you are instead electrically pointing it, and controlling the timing of electrical signals is a much easier task than controlling the motion of steel. All right, so let's talk about how interferometry works, to my forever shame and embarrassment in this room, but hopefully it's useful to some. Let's take a very simple case where we have two telescopes separated by some distance d along the ground, looking at a distant point source. So the radiation from that light we're going to treat as waves, and it is producing a plane wave that's coming towards both of them. It's monochromatic, so we're considering only a single frequency here. The electric field will induce a voltage on some wire in antenna 2 that looks like this. Some amplitude and a cosine as a I forget, left off the T. But anyway,
is that real or complex?
That's a great question. I defy Jonathan to tell me where I can see complex voltages on my voltmeter. It is a mathematical construction and convenience. There are only real voltages. Okay, so there's this voltage versus, I maybe just got cut off on the edge of the screen. Anyway, there should be a T there. And antenna 1 has the same plane wave arriving on it, except there is a time delay because it has to go further to get to this antenna, right? And that time delay is the geometric time delay here. It's just d projected, this projected separation or projected extra path length here divided by the speed of light. Okay, now if we want to make an interferometer, we don't just get two, voltages on wires. We have to connect them somehow. And the way that we do this in radio astronomy is we add a correlator. We take this wire here with this voltage, and we take this wire here with this voltage, and we multiply them against each other, and then we average. And that is not an obvious thing to do. When people talk about interferometry at shorter wavelengths, at optical wavelengths, they're typically superimposing the light from two telescopes and letting them interfere. They're adding. They're not multiplying. And so why are we multiplying? So let's work this through. We have F, we'll call it F for fringe actually, which is the time average, this part, of the product of these two voltages, this part. And I skipped a bunch of steps here that when I'm doing this in class, and I'm writing it on the board, I step through all the steps. But if you work out what the product of these two signals is, you can use trig identities to get yourself to this point where you've got the cosine of omega times this geometric time delay, omega being 2 pi nu, and then this other term that's cosine of twice the time frequency minus this geometric delay. And since we're averaging this, taking a time average of this signal, this rapidly varying part disappears. So the average of that goes to 0, and you're left with just that. This fringe is the voltage amplitude squared over 2 times the cosine of this geometric delay. And so you'll get a periodic oscillation. If your source is going across the sky, this theta will change, and you'll get a periodic oscillation as you go between, as you go through the cosine, because this number is changing. So here's an example of that. If you imagine that you've got a 1 gigahertz signal incident on both antennas, red is going to be antenna 1 and blue is antenna 2. If they're arriving in phase, if this is an integer number of wavelengths of extra path, then your multiplication and averaging, your multiplication gives you this. So the red and blue are superimposed. You can't see them. This is the square of that cosine. And the time average will put you at a fringe of 0.5. That's convenient. You've detected a strong fringe. If they're precisely out of phase, you'll measure an average voltage that's negative, because whenever one of them is always negative, and this product ends up always being negative. Inconveniently, it's possible for them to be out of phase by 90 degrees, in which case you're going to have an imaginary voltage of Jonathan's dreams. But you see that this product doesn't capture this information. The average here is 0, and so your correlator will spit out nothing. This is a bad outcome if it just so happens that there are times that that the separation between these two antennas in space means that you don't see anything. That's a bad way to measure what there is on the sky. And so in an actual interferometer, we do create a complex correlator. We take the signal from one antenna and add it, and this gives us our cosine component of the Fourier transform. And we take our signals and delay one of them by 90 degrees and make this product again so that this failure mode doesn't happen. We're effectively shifting one of these by 90 degrees so that we're always capturing the full signal. And we can express that as a complex number as a mathematical convenience, and it is quite a convenience, but the voltages are still real on the wires. Okay, before we make this interferometer any more complicated, let's talk about what this simple picture tells us about what interferometer resolution is. So in order to see that a source is moved on the sky, we want to move this term, this argument of the cosine function, by about 2 pi, right? And if you go through the math here, I mean, you know, d over lambda doesn't change, but the sine theta part will. You can find that the angle that you have to move by in order to get one cycle change in the argument of the cosine function is about lambda over d. So the resolution of this interferometer is determined by the telescope separation, not the size of each telescope. This is called the fringe spacing, and you know, quick hand waving was on the first slide, but there's, you know, 2 times 10 to the 5 wavelengths is a fringe spacing of 1 arcsecond. And so if you have baselines longer than 200,000, you're getting sub-arcsecond resolution. Murmur of question there? No?
Sorry, could you repeat that?
2 times 10 to the 5 wavelengths? Yeah. Okay. So a monochromatic interferometer is nice, but we typically, as I said at the end of my previous talk, we get sensitivity by increasing our bandwidth, right? That gives us more samples of the noise. And so we wouldn't want our interferometer to be monochromatic. We want to accept a larger frequency range. But what happens when we do that? Well, we can take the same fringe equation we had before, but now integrate it over a range of frequencies, a width of delta nu centered on some frequency nu 0. And if we do that, it's just the integral of this simple equation here. You can, you know, do the math yourself, but what you end up with is this cosine. This is the nominal fringe function here, right? At center frequency, everything looks like it did 2 slides ago, but it has this additional term that's a sinc term, sine x over x, and it depends on the spectral width. And so this envelope is going to suppress the fringe visibility. And you can see that if you calculate the fringe pattern for a range of wavelengths. So this effect turns out to be quite dramatic, and so I have to do this in order to make it easily legible with very short baselines. So here's a monochromatic interferometer. Its fringe pattern, it's an east-west baseline that's 30 wavelengths apart. And as the source tracks across the sky, this is 4 hours before it's due south, and this is 4 hours after. And I think I ran this for a source at 30 degrees declination and a telescope 30 degrees north of the equator, whatever, it doesn't matter. The point is, you've got this fringe pattern. It's not a perfect sinusoid because the projected baseline length changes. If you allow a 2% bandwidth, so if you take red being the central frequency plus 1% and blue being the central frequency minus 1%, you can see that those waves, which are going to get integrated together along with everything all the way in between, are out of phase, right? And so the amplitude of this, this fringe pattern is starting to be suppressed by that sinc envelope. And in fact, if you consider a 10% bandwidth at 30 wavelengths or a 5% bandwidth at 60 wavelengths, because it's the product of the D and the fractional bandwidth, you can see that you get this sinc envelope suppressing the fringe pattern quite dramatically, and so you'd only be able to see your signal near transit. And it gets even worse. You can go, here's the inner hour. Here I'm just allowing a 10% bandwidth and a mere 480 wavelengths, so this is still very large resolution on the sky. It's 400 arc seconds. And you're only detecting that fringe in the inner part here, and away from the center it's washed out by the bandwidth effect. Obviously this wouldn't be acceptable, and so there has to be a solution to this. And the solution to this is to ensure that we don't let this geometric delay complicate things. The problem with the geometric delay is it's a different number of wavelengths across your bandwidth. And so because we are going to have digital signals, by the end of this week you will have all sorts of digital signals, we can delay the arrival time of those digital signals at the correlator. Or before we had digital signals, we could delay the analog signal arrival time at the correlator with complicated tricks of waveguide and trombone tubes and so on. We call this delay tracking, and it's essential to the way interferometers work, at least at high frequencies or where we're trying to achieve high resolution. So that was the very simple picture. The derivation you usually see of interferometry gets you to a point where you understand interferometry to be a Fourier transform, and I haven't done that yet. This is the part where you perhaps want to enjoy the ride and not take notes if you were trying to take notes. Not that I've seen anyone do that. But let's take a simple case here, but let's go through the math for real. We have a somewhat idealized interferometer in that it's, for the moment, got all these simplifying assumptions. There's a very distant source. It's monochromatic. We're not going to concern ourselves with polarization, though that one's easy to fix. The source is spatially incoherent. This is also not a very significant assumption in astronomy. There's only very rare cases where sources are spatially coherent, where the signal here and the signal here are related to each other and are not random realizations. And also that there's nothing between the antennas and the source affecting the propagation of the waves. So we've got a source. It's in direction R. R1 and R2 are the directions from each of the antennas, but because the source is far away, they're the same direction. They're just different lengths. And it's emitting an electric field. The sky plane is x prime and y prime, and the ground plane is x and y. The antennas are on the ground. So let's do the interferometry thing, right? We're going to take the electric field measured at two antennas, and we're going to multiply them. The field, the equation for the field that we will receive at antenna 1 out here at x and y, shouldn't have primed though. Oh no, it's the field from x prime and y prime, is the field emitted from this patch of sky at a time t retarded by the amount of time it took for the light to get there, divided by z, the distance to the source, because the field falls off like 1 over r. And then there's this phase factor. The wave is oscillating, and so you've got frequency, and again, the oscillation is delayed by this propagation time. You can do the same thing for antenna 2. I'm not writing it out. We're going to, just like we did in the simple case, we're going to take the product of two things and average them. But we're going to call this the spatial correlation function. Because you can imagine that there are two antennas on the ground, but you could be putting the second antenna anywhere relative to the first. And you could define a function everywhere that is the correlation between the voltages received at this antenna and this antenna as a function of their separation in 2 dimensions. So that R12 looks like this. You've got this part that doesn't need a time average because the t's canceled. You've got 1 over z squared, and then you've got the time average of the 2 voltages. If the bandwidth you're sampling in a small, this is a complication, but if you're considering a relatively narrow bandwidth such that the propagation time difference is not large compared to the inverse of that bandwidth, then your wave can't wiggle much faster than that, because the speed at which your wave can wiggle is inversely proportional to the bandwidth. And so you can assume that the electric field is basically the same despite that extra propagation time, in which case the average of these two things is just the intensity distribution on the sky. Let's do some more simplification. We have down here this factor. Let's try and clean it up. We can, you don't need to write this down, but you can calculate what R1 is. It's just the length of this vector, so the distance plus the difference in between, x and the sky coordinate and y and the sky coordinate. Because these are small compared to the distance to the source, of course, you can, use very simple case that it's 1 plus epsilon square rooted is 1 plus epsilon over 2, and you can expand all this out. You can do it for R2. You can difference them, and what you'll find, because you've got these cross terms being squared here, is that you've got R1 minus R2 is 1 over the distance times these products of sky coordinate and dx, where dx is just the separation of these two in x and in y. There's these second order terms in dx, but, and through math that again in a hour-long lecture that was just on this you could work out, it's here too. If you're in the far field, if your wavefront is not curving significantly, then this is not important, and so you end up with R1 minus R2 simplifying to this product of sky coordinate and ground coordinate over z.
These are the separations between the antennas?
That's right. D is, the x separation and the y separation. Continuing, let's create some more convenient coordinates. So let's define L as x prime, the sky position, divided by the distance. So it's an angle now, right? It's how far is it off from what we're calling 0, our pointing center, divided by the distance. It becomes an angle. And m is the same thing in the y direction. Then the differential versions would be dl and dm, because these factors appeared in the integral before. And we can also express dx and dy not in meters or centimeters or microns, but in wavelength counts. So we can define u as the antenna separation in wavelengths, and v is the antenna separation in the y direction in wavelengths. And so if we do all that, we had this factor in that exponent before. We combine all the simplifications we just made, and suddenly we have something that looks like, are you giving me a time warning?
Only 10 minutes.
Oh, okay.
Is that good?
Yeah, that's fine. That's fine. Very unobtrusive. Very good. And so this whole thing simplifies to this product of baseline lengths in wavelengths and sky angles in radians, which is cool. This is simpler than that. It's just 4 letters. Let's put all that back into the equation we have. So I just made a bunch of simplifications, which hopefully you're not furiously scribbling down. If you haven't seen this before, you'll just get it off the slides later or look in the book. But here is that equation. This is what it looked like. Here are all the things we simplified, right? So this becomes that. Dx, dy become dl, dm once you absorb those 1 over z's. This becomes the intensity distribution on the sky, and we make it as a function of these angular coordinates now instead of the sky, meter coordinates, which is a goofy unit to think about on the sky. And when we do all that and allow ourselves to rewrite this equation with all the substitutions, we see that this spatial coherence function looks like the intensity on the sky times an exponent with a 2 pi I and some things, which is interesting. Because if we then integrate this across the whole sky, not just over this little patch of it, we have what we call the visibility, the sky integral of this thing that was the coherence function, which is a very Fourier transform looking thing, right? the visibility is the Fourier transform in 2 dimensions, as Deepti was getting to at the end of her lecture, of the sky intensity distribution. So we started by saying, all right, we have 2 antennas. We can multiply an average. Let's see what happens. And what happens is that we get out the Fourier transform of the sky emission. So that's what the interferometer is going to measure. This is often called the Van Sittert-Zernike theorem. This is discussed in good detail in Thomson, Rand, and Swenson, but that was actually a different thing, but the math is the same. And so it gets called that as a shorthand. There are many complications beyond what I've shown here. Of course there are. But the basic result is essential to understanding interferometry. So you can consider so many things. They're all in that book. So go look at TMS. But if your field of view is large, as it is for the experiments of many people in this room, then you have a curved sky, and some of the approximations I made don't work. In fact, I was quite glib about the way I was making them. It's possible, actually, that the far field, this wavefront non-curvature requirement, isn't satisfied. So if you were to take the EHT and try and look at the moon, for example, it would not be in the far field, nor would Pluto, nor would things within a parsec. So, the bandwidth you include at any instant in your interferometer and how long you integrate before resampling have to be carefully considered. There's lots of things that can make this far more complicated. But this picture helps you understand how interferometry starts. So having explained that interferometry is measuring the Fourier transform of the sky, it seems like quite simply you should be able to Fourier transform your interferometer data and get back to the sky. But it's not quite as simple as all of that. So, trying to think if I want to go through this, because I got to pick which parts of this I'm going to do. This was designed as a resource. Deepti went through this, but let's just briefly say, remember, we're going to measure the visibility function of the complex number. We're going to measure the real and imaginary parts. So you can think of your visibility this way or this way, because I'm going to plot it this way, amplitude and phase. So here is a point source. It's not on the center of the plot, but it's a delta function in the sky. The Fourier transform of a delta function is what now? The amplitude of the delta function Fourier transform is equal everywhere, but the phase changes. And so this is revealing one of the things about interferometry is that it's going to encode the position of this source with the phase of the complex visibility. If the source were at center, the phase would be flat. As the source moves away from center, this phase ramping gets more extreme. Another thing is that here's a Gaussian. It's 2-dimensional. The Fourier transform of a 2-dimensional Gaussian is going to probably be what? It's going to be a Gaussian. But this Gaussian, isn't at the center. So where's the visibility Gaussian going to be when I look at the amplitude? Moves faster if you answer. The amplitude of the visibility function will be centered where? Yeah, at the center. Because the phase is what's going to encode the position. So here's the phase. You see the gradient from this thing being off center. All this is just noise. But in this part, there's actual enough signal for the computation to work. This came through Myriad, and so you can see the gradient indicating that it's off to the off center. All right. The other thing that I always like to show is that if you had two sources that are adding, the Fourier transform is linear. This was one of the properties that Deepti introduced. You just add these two things. So the Fourier transform of elliptical thing over here and a circular thing over here, you think, all right, well, we'll just add them. But you have to remember that they're complex numbers, and each of them has a phase ramp. So they add in this weird way. And so you get these interference patterns through the Fourier plane. All that's to say that things that you think might be simple Fourier transforms turn out to be complex. And in order to reconstruct an image, you need to have all or a lot of this information. But unfortunately, interferometers don't measure all of the information. So interferometers, as a sort of near ending point for describing them, we often portray them in terms of their sampling in the Fourier plane, the UV plane. Which spatial frequencies are we actually measuring? We can only measure those that are given to us by the separation of pairs of antennas. And so, here's an ALMA array configuration, and here's what you get instantaneously from all the pairs of antennas in the UV plane. And if you let the sky rotate for a while, you can fill that in a bit more. But it's pretty good compared to what we were used to not very long ago. And so, what do these limitations mean? The largest UV distance you have is the largest baseline you have, which sets your resolution. The hole in the middle here is information you don't have about, because it's small in the Fourier domain, it's large in the sky domain. The large-scale emission is missing. An interferometer will high-pass filter the sky. This may or may not be important for your science. If you're looking at a compact point source, high-pass filtering it will always give you the same answer. If you're looking at a molecular cloud that's extended far beyond the scale of the interferometer beam, then you will miss an enormous amount of information. The Fourier transform of this UV sampling is what we call the dirty beam. It's like the PSF of the interferometer. So you take UV coverage like this, you Fourier transform it, you see that there's a bright central core that's compact, but that there's this oscillation as you move away that imprints all this structure. And you can see that if you add up the signal from lots of individual baselines, you can create for yourself a pretty good beam. So this is the beam of a single baseline. It responds to a sine wave, a plane wave across the sky. As you add a third antenna, you get a slightly more localized beam, and then 6, a 4, and then 8, and then 16, and now you have something that kind of looks like the sort of PSF you'd hope to have. And if you make the array larger, if you extend the antennas out further here or further in the UV plane here, then this beam will get even smaller. But you'll have more little side lobes, if you will, of your response. The last thing, I think I can. This will be a good place to end, I think. Deepti talked about the convolution theorem of Fourier transforms. So the UV coverage, our sampling of the UV plane, is multiplying the Fourier transform of the sky emission, the true visibility function, the thing we'd like to measure. We're only sampling it at specific frequencies. And so because they're multiplying in the Fourier domain, when we Fourier transform back to the sky domain, what happens? Yeah, so you convolve this ugly thing with your true image, which is just represented here as a point source and a faint extended source and another faint extended source, and you see that you get a blurred out version of that. And so correcting for this is, an enormous part of interpreting interferometer images in the case where your source structure is complex and unknown. And that's it. Questions?